I am Ajay Baranwal, Center Director at CDLe. CDLe is Center for Deep Learning for Electronic Manufacturing. It was founded 2 years ago by a partnership of Nuclear, Micronic, D2S. Today, I'm going to talk about a deep learning-based toolset for mask analysis that uses a digital twin. We built 3 tools in the deep learning toolset for SEM analysis. The first one is automatically filter good quality SEM image alignment for CAD to SEM, and defect classification for VSP mask writer. However, deep learning requires huge amount of data. It needs a lot of data with all varieties so that it can learn a meaningful model. We built SEM-based toolset. That means the huge amount of data has to be SEM images. Mask Shop does incredible job to not create any error in printing. So it's extremely hard to get SEM images. Where do we get a large SEM images from? For that, we built a digital twin to generate millions of SEM images. As you can see in the slide, we use a CAD data where we induce geometries, patterns, and also errors, and it goes through the digital twin, and we have generated SEM. The idea here is to train a deep learning model on generated SEM, and once the model is trained, to use it for production for real SEM images. Using the digital twin, we could generate millions of SEM images, including normal, geometry patterns, as well as defect. On the left-hand side, you can see a collage of generated millions of SEM images, and right-hand side, you can see some normal SEM images generated from the digital twin and with error as well. We also generated some curvilinear shapes too. Before I jump into my tools from the toolset, I would like to let you know that I'm going to follow a specific pattern for my presentation. First, I will go ahead and detail about the tool, then the training data which I used, and then followed by the deep learning model, and of course, followed by the results. So let me go to my first tool from the toolset. It's automatically filtering good quality SEM images for test chip. For test chips where through dose and through pitch patterns can go beyond the process limit of printability. In those cases, some of the features may not be printed on the mask, or they may be badly printed. SEM images with this kind of feature must be discarded for applications like CD extraction. This tool does exactly what is desired for the test chip. We built a tool for automatically filtering only good SEM images for the test chip, and we wanted to do it fast. The rule-based methods, they do not do pretty good job on SEM images because of the varying lighting conditions, contrast, line edge roughness. And also, if you do it manually, it's going to take a long time, hours of time. In fact, for our purpose, we had a set of SEM images having 4002 images, and to manually filter them, it took 4.5 hours. Actually, that was also required for the test data, which you'll see here. For this model, for this tool, the deep learning model only required 2,700 images, which was acquired by customers. These were good SEM images. And for the test data, we had 4,200 images, which were manually labeled. And that's the test data, which took 4.5 hours. Our goal was to use deep learning so that first we can reduce the runtime for the test data to minutes instead of hours. Also, to get an accuracy no less than 90% with a low false negative rate. That means a good SEM image should not be rejected. The deep learning model which we used is called deep autoencoder, followed by an anomaly detection network. As you can see here, there are two networks, one encoder and a decoder, part of the autoencoder. These are two neural networks. It takes a good SEM image and create an embedding, and after the decoder, we get the constructed SEM image. A reconstruction error is taken. For good SEM images, reconstruction error will be low, and for bad SEM images, the reconstruction errors will be high. Using the embedding and the reconstruction error, it was further fed to an anomaly detection network, which outputs a probability that a particular image, SEM image, is good or bad. Using that probability, we could filter out the SEM images automatically. That too with 94.5% accuracy and a very low false negative. And on our workstations, it took only minutes, which has one average GPU instead of 4.5 hours. This was pretty incredible. Now I will move to my second tool from the tool set, which is CAD to SEM image alignment. Applications which require CAD and SEM, they need the features to be aligned on CAD and SEM images. And as you can see on the left-hand side, I have an example of a CAD and SEM. They are overlapped together. And the reason you see some solid and overlap and some blurry means there are misalignment. Once the CAD is aligned to SEM by shift, rotation, and zoom in or zoom out, in some case, you see on the right-hand side a completely aligned CAD and SEM image. And you see 3D looking solid impression. There is no blurriness. This is what we want. Now, existing methods to do image alignment, they fail to do a pretty good job, especially in cross-domain images such as CAD and SEM. And that's why we built a deep learning-based tool. For the training data, remember the previous tool, the automatic filtering, it did not require a lot of training data. After all, not all the deep learning requires huge amount of training data. There are some exceptions. However, for this case, it was required to have at least 700,000 SEM images. And where else could we get it from? We cannot get from the mask shops. So we did generate them using the digital twin. 700,000 images for training data and 70,000 for test data. And we manually aligned images for testing purpose. The deep learning model for this uses convolution network and a registration network. It takes a misaligned CAD and SEM pair and aligned CAD and SEM pair. It goes to the network. Network learns the spatial transformation in the form of shift, rotation, and zoom. and based on the difference, it uses a loss function to train the network. Once the network has been trained, we see pretty good results. Similar image here, before alignment, which has solid and blurriness, and after perfectly alignment, we have only solid impression. Now for quantitative measurement, we used a score called NCC, which means normalized cross correlation, and a score of 0 means complete misalignment, and a score of 1 means full alignment. And our goal is to get the NCC score for the images very close to 1. In this case, we get a 0.99 score, which is pretty good. I have another example with different patterns. NCC score is close to 1. Yet another example, even another example, and the last example. This was also very interesting and promising. And in fact, this tool was used to enhance our digital twin. Now with this, I will go to my third and last tool in the tool set, which is a VSP mask writer defect classifier. VSP mask writer is very reliable machine which runs 24/7. Occasionally, there may be some malfunctioning, and for the mask shop, it is important to identify those errors, debug it, fix it, and put the machine operational. For this purpose, there are human experts who use SEM images to identify if there is a problem with the mask. We created a deep learning based tool which can help expert to identify the defects. Oops, sorry. Another thing I would like to mention here is that we use the first two deep learning tools to build this one. We use the filter and the image alignment for the third one. It's kind of building deep learning tool stack, one on top of other. Before going to give more detail about the VSP writer tool, I would like to explain the architecture of the VSP writer system. There are principally three components, as you can see from the picture. The top has an electron gun, which emits electron beams. Then the first upper portion has a shaping aperture and shaping deflector. The shaping deflector, the upper part, it is responsible to create shots for rectangular and triangular shapes and also determine the size of it. And the lower portion, which has another shaping aperture and deflectors, sub and main, responsibility is to be able to print the shot on the reticle or the mask based on the desired position. If there are some problem with the electron gun, it can end to a dose error. Problem with electron gun can have intensity variation of the dose. And in this case, on the right-hand side, as you can see, because of the decreased dose intensity, the geometries are shrinking. Another type of error could be shape error, which happens because of the shaping deflectors. If there is some problem with the shaping deflector, the shots, the geometries of the shots, the rectangular and triangular, can get distorted. In fact, you see distortion on the edges of the shape. The third type of error is the position error, which could be caused by subdeflector. And if there is a problem there, then the geometries, the shots will not be printed at the desired location. there could be a error, deviation. It's called position error. Now, all three types of error, dose, shape, and position, it needs to be identified and debugged and fixed. We build a tool set to do that. However, before training the deep learning model, we required millions of SEM images, and we generated it from the digital twin. We use all three types of error to the training data and normal. And for the test, we induced certain errors and then printed it with the machine and manually labeled. The model which we use is a typical classifier model, which is convolution network based. We tried VGG network, ResNet, and settled down on a custom ResNet. Custom ResNet had custom convolution layers having skip connections across layers. The model takes a reference SEM image and a defect SEM image and outputs a probability that this error belongs to one of these three types of error. We saw very positive and promising results, and I'm going to show some of the examples from the results. In this case, on the left, you see a position error, a reference and defect SEM image for the position error. And on the right-hand side, you see the probability spit out from the network, which is 99%. In the middle is the interesting thing. It is a heat map of what does the deep learning network see. It does see a red and high intensity color map for the region spot where the error is. So the network is not only giving a high probability for the position, but it's also focusing on the spot where the error is. This gives a very good confidence on the network. Another example for the shape error, we have a high probability for shape, and the network focuses on the spot where the error is. In this example, network gives almost equal probability to dose and shape error, and also focuses on the right spot where the network sees the error. However, as the network is confused, it turns out that this kind of error is even hard to discern by human expert. There are other information needed to make good diagnosis on these errors. So with this, I would like to conclude my presentation by saying that deep learning is extremely powerful for the SEM analysis. The three tools for the first as filtering good SEM image, the CAD to SEM alignment, and the defect classifier. It shows extremely well results, and it was only possible because we could generate millions of data, not just in number, but covering different types of the printing, whether errors or a bad SEM image. It was all possible because of the digital twin. And also the digital twin used deep learning, another type of deep learning to make it. So deep learning, along with the digital twin, is extremely powerful for SEM analysis. Thank you for listening.